Welcome to our deep learning workshop. Basically, we're going to be explaining the deep learning process and applications that deep learning has to the real world. So first of all, what is AI? AI basically stands for artificial intelligence, which basically means the ability of computers to mimic human intelligence. Basically, they're trying to simulate human thinking and behavior using computers and machines. So deep learning is like a category or subcategory of AI, but basically they're trying to train models to learn a task to solve a problem. And deep learning algorithms are developed to learn patterns from larger amounts of input data. So basically in deep learning, there involves models or algorithms, which are basically structures that humans code in order to help solve a task. And they also involve input data, which can be anything from videos, images, audio, etc. So why do we use deep learning? Deep learning can solve a lot of complex tasks. For example, they can do tumor identification from millions of images. They can do small object detection from complex pictures. For example, if a camera is trying to scan the beach for trash, they can then take pictures of the beach and then they can identify the smaller pieces of trash. They can label that and say, oh, well, in this picture, there's a small piece of plastic that's in this picture. Tumor identification, it's sort of similar, where basically they take pictures of different types of tumors and then they like maybe draw a circle around this tumor and say, oh, well, in this picture, we see a tumor right here, which basically means that it can use computer vision to basically identify things in pictures. Deep learning is also very efficient because models can be trained in very little time. Depending on what model it is, it can be trained in a few minutes to a few days, and it can solve tasks in real time within seconds or minutes. For example, if we train a CNN model, which we'll talk about later, for example, it can classify 2,000 images into 10 categories, and training might take 10 minutes. In real time, it might classify these images in a few minutes. For example, if there's cats and dog pictures, it can then sort them into these categories within only a few minutes. Deep learning also saves human effort, because otherwise humans have to manually go through these thousands of images to identify or classify things, which is very time-consuming. So one example of deep learning and how it's used is that if given a lot of numbers to identify that a number is 3, a deep learning model processes images of different numbers from 1 to 10, and then they identify these patterns and shapes and edges of each number. For example, they memorize that 3 looks like that, 7 looks like that, for example. And then from a lot of training, then they can identify what number is what. So this is the entire process of deep learning. Basically, first we have to obtain the data, which basically means to find, import, and process a data set. We can find data sets from a lot of places, like for example, Kaggle has a lot of free data sets of different images, videos, etc. that we can use. The next step is to segment the data to split it into train and test, or X and Y, where basically it's trying to tell the model, well, we can first train the model on part of the data and then test the model on another part of the data. After we segment the data, the next step is to create the model or code the model. And then we train it, run it, evaluate it, see how accurate the model is, and then try to optimize it or improve it by trying to change the model's parameters and things like that in order to make the model have a better performance. So what does the deep learning process include in detail? Well, first of all, the goal is to perform these tasks without human intervention. A model can, for example, identify images, can basically classify things without human help. It only needs human help during the training process, but in testing, it needs to rely on itself to learn and then see what to do, like for the task. Like for example, they need to classify these things by themselves, identify these things by themselves. So for the dataset part, like I mentioned before, you can find them online, like for example on Kaggle, or you can also make your own. For example, if you're trying to identify pieces of trash on the beach, for example, there's different types of trash, like for example, plastic, bottles, cans, etc. You can find images or take pictures of images yourself of these types of objects and then sort them into different folders like in Google Drive and then import them into some kind of Jupyter notebook, like for example, Google Colab. So then you can create your own data set in order to train a model on these data sets. So like I said before, you can process these data sets into a Jupyter notebook. Other types of Jupyter notebooks include Kaggle too. Kaggle not only has data sets, it also is a notebook environment that you can basically import models into, or no, import data sets into, and also put or train models on Kaggle as well. Basically, Kaggle can support the language of Python and R. Basically, you can code those models in Kaggle to train your models on these data sets. So for example, if we load the ImageNet dataset, basically ImageNet is this really large dataset that has a lot of images of different types of objects, like for example, animals and plants and things like that. For example, for that one, we can load it into Kaggle and resize all the images to 256 to 256. So one reason why sometimes we would resize them to all the same size is so then it makes the model less confused based on the sizes, because we don't want the size of the images to affect the model's training, because the size of the image doesn't matter. What matters is what's in the image. So basically, in order to make the model less confused and also make streamline the process of making the model actually learn images data, we can resize it to all the same sizes of the images. Next, we would split the data set into train and validation, or train and test, or basically, for example, we could split it to 75% train and 25% train of the data set. That basically means that if we have 100 images in our data set, 75 images are used for training and 25 are used for testing. And basically for the model part, we could code any type of model that we want. For example, CNNs, RNNs, etc. Usually CNNs are really good for images, and RNNs are really good for audio or text, for example, in trying to translate languages. Basically, the goal is to improve the model's ability to solve problems. For the very last step, after we train these models, we can then optimize the models to, such as by changing their parameters to improve its performance. For example, for CNN, you can make the size bigger, or you can make the CNN model smaller to increase its classification accuracy on ImageNet or any kind of other datasets. So here's some types of deep learning tasks. They're supervised, unsupervised, and reinforced. Supervised basically means that we use training data that is labeled. We tell the model that this picture is 3, this one's 4, etc. Basically, already in the data set, there's already an image, like for example, an image of 3, and the label, which basically is 3. Or maybe if there's already a dog image, below that, we say that the label is a dog. And basically, that basically helps the model in seeing, oh, well, we're associating this label with this image, and therefore we can then learn that and memorize that. And that's what the model is trying to do for supervised. Of course, for the testing part, not the training part, but testing part, of course, the model has to predict the label from the image. So basically that means that in training, for example, the model can see that there is a dog image and that label is a dog. But in testing, the model has to be given an image only and then predict the label. For example, if given a cat image, it has to predict by itself that, oh, this is a cat. So unsupervised basically means that the training data that's given to the model is not labeled. We don't tell the model any information about this data. For example, we're giving it cats and dogs without telling them that they are cats and dogs and have the model then classify them that way. I was assuming it might be a little bit harder for the model, but eventually they will be able to learn. So for example, if we don't tell the model these are cats and dogs, we just give them a lot of cats and dogs images, eventually maybe based on pattern recognition, the model can then subdivide them into different types of categories. For example, maybe dogs usually have rounder ears in these images and cats usually have pointier ears. And based on that pattern recognition, then the model can sort them into the categories, like saying, oh, all pointy ear pictures will go into the cat category, and then all the rounder ear pictures will go into the dog category. Lastly, the very last task is called reinforced, or reinforcement learning. That basically means that the computer learns from trial and error to come up with the best possible solution based on rewards or penalties for each of its actions. This is very like training a dog. For example, if a dog can jump through the hoop, then we give it a treat. If the dog does not jump through the hoop, then we do not give it a treat. Another example is that in self-driving cars, we can train like some kind of agent to optimize the paths of it driving on the road to plan the most efficient paths. For example, there could be 3 ways to get from home to school. But if we have the self-driving car kind of learn that this way is the shortest way, the most efficient path to school, then we can reward the car or things like that. So then next time it will always remember to plan the most efficient path and not take the longest path. Basically, it's sort of like trial and error. It's also sort of like based on rewards and penalties. So like, for example, maybe the cars get penalty if it accidentally chooses the wrong path or chooses the longer path. So here's some applications of deep learning. There's facial recognition, identification, and detection. For example, in emotion detection, in the very left picture, we can maybe see that, oh, this person is smiling. So then this is kind of like emotion. We're basically given pictures of people smiling, laughing, frowning, things like that. then the model can identify their emotions, like someone is sad, someone's mad, or someone's happy, and things like that. This is very similar to just image recognition, but more so with emotions if we give it humans expressions and things like that. The second one is identification, where basically you can identify objects within an image. For example, in this one image, the model can then see, oh, there is a dog, bicycle, and truck. And they can then put a bounding box or like a label over it to tell us that this is what they learned. They learned that this is the truck, this is bicycle, and this is the dog. Of course, there could be a little bit of inaccuracies. For example, the car is more like a van than a truck. But of course, maybe we're not giving it enough data, so that maybe it doesn't know the difference between truck and van yet. But if we give it more images of trucks and vans, maybe then it can identify, well, the picture is actually a van, not a truck, or for example, things like that. For detection, this is sort of like with tumors or in terms of like diseases, cancer, and things like that. Basically, if given like an X-ray image or any kind of other types of scans, you can identify the small part that is a tumor, that is like a non-healthy cell from like the other ones. For example, if we're given this image, it can then identify, oh, that part, that blue part is like the tumor part of the image. So here's basically talking about the future of AI in general. So we don't really know if this will happen for sure, but basically we can probably predict that these things may happen. So maybe in the future, robots might be replacing human jobs, like for example, with cookers and chefs. If robots can, for example, already know how to turn on the stove, know how to like flip a pancake or things like that, then they could probably learn basic human like cooking stuff and things like that. Eventually they could be learning like harder recipes and things like that. So eventually robots might be replacing humans like chefs and cookers and things like that. In the future, it could also cure genetic diseases, maybe through more like detection, more like identifying there is a tumor here. So then if they kind of detect that really fast, then the humans can get more faster treatment after they can already be identified, oh, they do have a tumor or they do have skin cancer and things like that. Cures, maybe it will be a little bit harder though, just because genetic diseases are still pretty new in the medical world. We're still kind of like, we're just trying to find like we're still trying to find cures, we're still trying to find solutions to that and things like that. So I'm guessing that it'll be a little bit easier for AI to learn how to detect and identify like the initial steps of trying to detect someone has a disease or things like that. It'll be a little bit easier for AI to do that first and then maybe do curing later. And eventually we'll be having more robust and well understood data, because if we're recording a lot of data right now, in a few years, we'll be having like thousands or millions of images of different things and things like that. And that will help the model learn more, because the trend is basically that if you have the more data you have, the more accurate the model can be. Because like, for example, if we're giving the model only like 3 images of dogs and cats, the model still doesn't really know the patterns yet. But if we give it 1,000 pictures of dogs and cats, it'll be a lot easier for the model to then understand the patterns within these images to know that they are dogs and cats. Basically saying with this more types of data and more types of robust data, more amounts of data, then that will help the models become more robust and more accurate and things like that. So here's another walkthrough example of a deep learning task. So for example, if we're trying to identify if the picture has different types of objects, first we need to input the data. You have to, for example, find a data set that has pictures of cats and bikes, and then train a model on these images. And then the output is to see if the new picture, the model can identify it as either a cat or a bike, or in this case, it can identify, does this image have a dog or a bike in this image, and things like that. So here's basically what the code of some models might look like. So for example, to split the data into X and Y or train and test, this is basically a common function used in Python. It's called train test split. So here basically we're feeding it 4 variables. So I think what it means is basically, so what I mentioned before is I thought that X and Y means train and test, but it actually means different things. So train and test basically means we're splitting the data into training and testing. So we train the model first and then we test the model. So actually X and Y basically means the images and labels or data in the labels. So X is like the actual images or the actual words, the actual audio, actual videos, or things like that. The Y is the label of it. For example, if X is cats and dogs images, the Y is the label, this is a cat, this is a dog, and things like that. So we're splitting it 4 ways: X train, X test, Y train, and Y test. We're using that function and we're splitting it up. So here, this basically test size 0.4 means that the testing batch is 40% of the data set, And then the training part is 60%. So like, for example, if the entire data set has 100 images, test size basically means there's 40 images that will be used for testing and 60 images will be used for training. So a rule of thumb is that it's not always the most accurate for every single type of model, but usually you want to have more images for training than testing, because the more you learn, the more you can do on your tests. It's kind of like math tests, where basically the more you train yourself on these types of math problems, the better you can do on the test. Basically, that's why usually researchers will be using more images for training than testing, which is why the test size is usually less than 0.5. Random state basically means, like, for example, we're giving it like a random, we're like kind of like randomly assigning which images will be training and which images we put in testing and things like that. So then here's like a models, basically like the code of the model. So actually we had a question in the chat saying, what is random state? I think random state is basically like the variable that basically tells you, oh, to assign these images randomly and things like that. 101, I think, is just like an arbitrary number. But basically, we're telling this function to make sure to put the training test images randomly. So for example, if you're given like a 100 image data set, maybe random state is kind of like saying, oh, well, we don't really care what order these images are. We just want to randomly assign 40% of the data set to testing and 60% to training. So then the next step is basically to code the model. So here's an example of a CNN model's code. So every single model will have different types of code, but this is like one example of a CNN or convolutional neural network model. They're using like the Python code and also using the Keras library, which is why there's sequential and different types of functions right there. So basically, the first step is to add, of course, like a convolutional layer. So here, there's like a layer that says com2d, and then it has different numbers inside. Basically, this means that this is like the size of the convolutional layer, the first layer. It's like, oh, 64 in size. And then 3x3, it's like the kernel size. The kernel size is basically the kernel that scans over the data. And basically, it's kind of like the scanner that can identify patterns and things like that. So in this case, they're saying the kernel is 3x3, like the size of the kernel is 3x3. And then, of course, in the next few workshops, we'll be going more deeper into code. This is more like a beginning process type of workshop. It's basically, these next steps are basically just adding different layers of convolutionals or convolutions into the model. So in this case, the CNN has different, let's see, it has maybe like 4 convolutional layers, and there's different types of layers in between these layers. And also at the very end, the most important thing to note is that if it says dense 7 at the very end, this most likely means that this model is being trained on a data set that has 7 types or 7 categories. Maybe there's like 7 categories of fruits, 7 categories of plants, and things like that. And then the very last step is to basically run the model or train the model. And here, because we're using the Keras library that's built into Python, we're using the function called model.fit. Basically, that just means to train the model on these data sets. So here we're putting in X train, Y train. The number of epochs is basically sort of like the amount of times that the model looks at the data. So we're giving it 100. So then the model basically has sort of 100 times to look at the data to kind of like train and learn patterns from the data set. So that's why we set epochs to 100. Usually you want to have more epochs because then you want to give the model longer time to be training. Of course, you don't want to be putting too many epochs because then the entire thing will be running forever. But you also don't want to give it too few epochs because usually the accuracy rises with the number of epochs. And then here, there's basically other functions. Like, for example, this variable is called batch size, where basically it means that you're looking at 16 parts of data at one time. So if the data set is like 100 images, where the model is looking at 16 images at a time when it's scanning over these data and things like that. And basically, validation data is like the testing part. So here we're putting in the training part of data, and here's the testing part of the data. And here, if we run that function, we can then see the model's accuracy and see the model performance and things like that. So here's some resources to use that I mentioned sort of before, but also a recap of the resources. So with Kaggle.com, you can find import and process data to train and code models. You can also use Kaggle or Google Colab. Both of them are called Jupyter Notebook environments, but basically it means that you could put code in there and then you can run the code. So basically in these two platforms, you can, for example, use Python or the R language to train and code models in there. There's also the Keras and PyTorch library. These are basically libraries in Python that basically they have built-in functions where you can basically already code a model based on these functions. So it'll be a little bit of less code if you use these libraries to create a model to train something. So basically there's basically called like frameworks to code your model. Keras, for example, has different things like sequential, conv2d, activation, things like that. You can just use those types of functions in order to build a model. Other Python libraries include pandas, numpy, keras, etc. Usually numpy is for numbers and matrices. Pandas is for data sets. Usually try to like load in a data set. For example, if the data set is in table format, you can use the pandas library to kind of process that data set into like a table function or like a split into like a table or things like that. And then if you want to have more like tutorials or articles to read about deep learning, you can go to Torrance Data Science or Medium. They have a lot of good articles on deep learning, machine learning, and things like that. So here are the sources that we used. And thanks for listening to our workshop.